you were supposed to have read the JosEPHus problem by now. Can somebody summarize quickly what the JosEPHus problem is? And this would go well with our religious discussions. Yes?
We have n people in a circle, and one person stands with a gun and kills the K minus first person from him, and then he passes the gun to the person next on the circle. And this continues until there's only one person left. It's kind of like that penny problem.
So you first shoot and you kill the kth person. And when you kill the kth person, now the k plus first person has the gun and now starts to shoot. And this person will then shoot the person, k down. Or I guess technically you're moving k minus 1 down. And then you shoot again. Okay? So this is close to the standard JosEPHus problem. I think the original one, I think you killed every other person. You shot with 2. Or was it every third in the original? Okay, third one was every third. Lots of variants you can do. So one variant is you want to have yourself and your friend survive. Yes?
I know the answer.
Okay.
Gun control.
Well, no, if everybody had their own gun, then the problem would be very different. Right? So somehow they've entered into a suicide compact. And then they're going to keep going around like this. Something like that. So you want to figure out where should you be sitting so that you will be the one who survives. Or the next step, where should you and your best friend be sitting so that the two of you survive? Or more generally, if you have K people or L people, it should be different than this, where should they be sitting so that everything survives? The reason I said, of course, K is that at some point you will not be able to keep playing the game and have everybody survive. Other nice variants you could do is rather than having a person definitely killed, maybe they just have a probability of being killed. Or maybe the gun has a certain number of empty chambers and a certain number of open loaded chambers. And every time the gun kills somebody, you've now lost a bullet. And then this becomes a little bit more probabilistic and dynamic. Now where do you want to sit? So there's lots of fun variants you can do with this. What's the first thing you should do in a problem like this? Small cases. So we'll take k equals 2 and then do a bunch of different values for n. So one of the things I've been talking about is that eventually I want us to pivot and go back to doing Project Euler and coding and computation. I think coding and computation is extremely important. I know every time I try to have this capture this is not going to work. Let's see if that will work. So if I'm trying to see if I can get it to capture the screen. All right, so what I've done is I've written a program in Mathematica to calculate the JosEPHus problem. For the most part, it works best in terms of calculating things when k equals 2. You can do it in more generality. And then when you have something like this, you always want to decide how much do you want to output. I'm sorry, question?
Is the 4 ever speak? The 4.
Which one?
4 ever in the comment on the
Oh.
one. Yeah.
Yeah, some of these comments were written at various states of lucidity. You can probably tell by my spelling. There is no way that I will get permission to play this game on campus, so do not worry. And so when I do code, I actually like to put in a free parameter variable called printall or something like that. And so I can very easily determine which statements get printed out. And what you can do is you can actually assign different values. If the printall is 5, you print out everything. If it's 4, you just print out various things over here based on how much do you want to have outputted to try to understand what's going on. And so for instance, if I scroll down a little bit, so somebody give me a number of people.
27.
27. All right. And so what we'll do is we'll print out everything. And so it runs through, and here's your first 27 people. Then we start killing. And not surprisingly, all the even people die because we're taking k equals 2. And so in a situation like that, all the even people die.
Now we're even.
And now we have 1, 2, 3, all the way up to 25. 27 is still alive. 27 has the gun. And now we start playing. And so who's 27 going to kill?
3.
Nope.
7.
Nope. 1. 27 kills 1. It wraps around, wraps around the circle. And so now 27 kills 1, and we keep playing. And so now 1 dies, then 5, then 9, then 13. And now we get 27, 3, 7, 11, 15, 19, 23. And then 27 has the gun, 27 will kill 3, and this will keep propagating down like this. And so we see at the end that the person who survived is the person in spot 23. And then what you can do is you can play, well, instead of doing 27, what if we did 231? Not surprisingly, it takes a little bit longer. You start going through, and we see this time the person who survived was the person who was in seat 207. If I do 23 people, now it's the person who's in 15. And the question becomes, how do we figure out who survives? We want to collect data. What happens on the first step? All the evens die. So when we're trying to understand what goes on, this gives us an idea of how we want to collect our data. How should we be collecting our data?
Small cases.
Well, small cases, but which ranges?
Oh, in like single rounds.
Well, I need a starting point and I need a stopping point. So I claim if you think about this, the fact that all the evens die together on the first round, this gives you some idea of how you should be segmenting your numbers.
You want to like see which will like be in even spots.
Well, but you need to give me a starting value. So I did 23, I did 27. I want to know, I want to go from some starting value of n to some final value of n. And I claim there's natural divisions to do. Any thoughts? Okay, but which range? So you got to give me a...
For the second one, for example, you could consider things that are in the same congruence class as your capital N mod 4.
Okay, so we've got mod 4. What else could we be doing? So I claim...
In each round, when you do mod 2 to the k.
So I claim powers of 2 would be a very natural way to fragment the data here. Because if you think about it, you're removing all the evens. So you're essentially almost like dividing by 2. So if I start off by going from numbers that are between 2 to the 4th and 2 to the 5th, after I do this once, I'm now between 2 to the 3rd and 2 to the 4th. And there's a recurrence going on here. That if I know what happens, I know what's going to happen at a smaller value. So what I wrote is I wrote the binary JosEPHus search. You input 2 powers, and it will calculate what happens going from 2 to the power 1 to 2 to the power 2 minus 1. And so, for instance, here's what happens going from 2 to the 1st to 2 to the 2nd. The survivors are 1 and 3. Instead of going up to 2 to the 2nd, let's go up to 2 to the 3rd. So in the first range, I have a blank line every time I do a full power of 2. So if you look at the n, I have 1, 3, then I have 1, 3, 5, 7. Instead of going up to 2 to the 3, let's go up to 2 to the 4. Hopefully this will be somewhat visible on the computer. And now when I do this, 1, 3, 1, 3, 5, 7, 1, 3, 5, 7, 9, 11, 13, 15. So this is hopefully pretty clear in terms of what the pattern is. I'll do one more. And now we went all the way up to 15. The next one goes all the way up to 31. So again, when you can develop some data and get a sense of what's going on, if you can write some code, this can be extremely useful in terms of trying to figure out what's happening. And so, after the green chicken is done, we're going to still do a little bit more in terms of getting ready for the Putnam. But I do want to go back and do some of the Project Euler problems. I do want to talk a little bit about how you would write code to do stuff like this. If you can write some very simple simulations, it is extremely valuable in terms of getting a sense of what's going on. At this point, the pattern should hopefully be clear. It seems like we write our numbers 2 to the n plus L, And then depending on where L is, that's going to collapse in a very nice way and give us the answer. Right? All right, so I will post the code there. Let me turn this off, we don't need this anymore. Okay. What other proof techniques do you think might be useful for this problem? Induction, right? When in doubt, try an inductive argument. Why might induction be nice here? There's ends in lots of problems. Of course, induction is used in lots of problems. Yes?
Whenever you kill somebody off, you move to a smaller end.
Whenever you kill someone off, you move to a smaller end. In a few years, we will not be able to describe the JosEPHus problem like this. Sorry. So when someone is killed, you move to a small one. So now the question is, how many people do you want to start with? Do you want to start with an even number or an odd number? Which? An odd? Why an odd number?
Because from an odd, there's no way to get to.
So if you start off with an odd number of people, when you go through it once, you're going to be killing a lot of people, and then who gets the gun again? So let's see, we start off with 1, 2, 3, 4, 5. So here's our people. Now let's do 7 people. Sadly, there were some children. Right? And so...
This is terrible.
All right, fine.
Oh, I thought you were writing alley.
No. No.
Too far.
All right, so first 1 shoots 2, 2 is dead. 3 now has the gun, shoots 4, 4 is dead.
Like you really expressed the emotional trauma they're going through.
4 shoots 6. And now who has the gun again?
7.
And 7 has the gun. So it's not the same person as we started with. Okay. If we had an even number of people, who has the gun? 1. So for me, I actually like having the even a little bit more because it starts us with 1 again. And so this is an extremely useful thing in analyses like this, is trying to keep track of who has the gun, what configuration are we in.
Wouldn't it be easiest to look at a power of 2 because then the first person always stays with the gun?
Well, so the power of 2 is going to be the easiest one to analyze. And in fact, who survives with the power of 2? 1. And then the question becomes, what happens as you start adding people? So one thing in a problem like this is to always look and see, is there a point that's easy to understand? And then from that point, can I build on other things? And so if we have a perfect power of 2, what's nice is every time we have an even number of people, after we complete a whole cycle of death, we are back to where we started, with the same person having a gun. So in terms of the game state, you always want to keep track of the number of people and who has the gun. Okay? In problems like this, it really matters who has the gun. It's not just the number of people. Now, what if the person who has the gun is not the person you want to have the gun? Is it a big deal? Without having people getting into too much of the metaphor and violent stuff over here. Let's imagine that you want person 1 to have the gun, but unfortunately we made a mistake. We started with 7 people, and this little kid from Amherst
Oh, it's the same thing. Is there a
has the gun now.
renumber them?
So we can renumber them. Right? So if the person who has the gun is not person number 1, you can just renumber. It's not bad if you only have to do it once. The difficulty is if you have to keep renumbering. The more times you keep renumbering, the harder the problem is going to become, because you've got to somehow keep track of this all. Does anybody know anything that's really good for keeping track of changes like this? What subject? I'm sorry? No.
Computations.
Computer science.
Like what do you like
Philosophy.
No.
Math.
Statistics.
It's one of the only prereqs for this course.
Linear algebra.
Linear algebra, right? Yeah, trying to keep track of linear algebra is a prereq for this course. You know, trying to keep track. Linear algebra is all about writing things down in a convenient basis. In some sense, that's what we're trying to do here. Is we're trying to keep track of what's going on. So what was suggested is that if n is 2, maybe to the n like this, we'll mix up the little n and big N, then we know what happens. So who survives? So person 1 survives. It turns out we can now solve every case from this one observation.
Write a number as the sum of powers of 2.
We could write a number sum as the powers of 2, or we could actually use induction and we could walk down. And so after this wonderful, groundbreaking success with 2 to the n people, what should we consider next? 2 to the n plus 1. So now we have n equals 2 to the n plus 1. What do you think happens here? Who do you think wins?
Last guy.
Why the last guy? You want to close the door or have them become quiet? Either one is fine. Thank you. So let's think about what's going on now. We have 1, 2, 3, 4, 5, 6, 7, 8. If we had 8 people, person 1 would win. Okay? And how do we know who person 1 is? How do you know who person 1 is? They start with the gun. Now we have 9 people, and person 1 has the gun. We do not want to be in a situation with 9 people with person 1 having the gun. We want to be in a situation with 8 people and somebody having a gun.
So as soon as he shoots someone.
As soon as person 1 shoots somebody, goodbye person 2, person 2 is now dead, right? 2 is gone. And now person 3 has the gun. We're now in a situation with 8 people. I should not view person 1 as living over here. Where should I view person 1 as living? All the way down to here. I should view person 1 as living there. And now we're in a situation where we have 8 people and person 3 has the gun and starts the game. Who's going to win this game? Person 3. So because we know this situation, we now know this situation. You can write this formally, and I'll give you links. I think the book, I hope the book went through the detailed analysis of this. Okay. Now building on our success when n equals 2n plus 1. So what we should do is we should keep track a little bit of what the answer is. And so we have 2 cubed, and it was the first person. 2 cubed plus 1, and it was the... So the next one we should look at is 2 cubed plus 2. So now, unfortunately, we now have 2 people more than 8. So 1 has the gun, 1 kills 2. 2 is now dead. Who has the gun? What does 3 do? Kills 4. 4 is now dead. Now who has the gun? 5 now has the gun. And what do we do with people's 1 and 3? Put them in the back. And now we put 1 and 3 over here. Now we have 8 people with person 5 starting with the gun. So who wins? 5. So notice that we are getting this just from knowing one special case, knowing what happens with powers of 2. And the nice thing about powers of 2 is if your number is even, whoever starts with the gun after one cycle ends with the gun. So again, one of the whole points of this is to try to teach you techniques that will work again and again and again. This is similar to something we've seen before. This is similar to the stuff we were doing with game theory with the 2 players, is looking at complete moves. And here, a complete move is one pass through the chain. And then looking at what is the configuration after a complete move, after one pass through the chain. When we were doing the game of Chomp, and we just had the row and the column, we had this beautiful symmetry. Whatever you do, I do the same. And if we start off with the same number, I can force you to take the poison circle by just this kind of playing off of each other. It's a very similar principle here. I'm doing the analysis in one special case, the case of perfect power of 2. All right. If I now had 2n plus 3, the only thing that would change is now we would have another death, and now person 7 would have the gun. So is it clear that this is going to work all the way down to the end? Or is there going to be trouble at some point? Bless you. So in the case we're doing here, we're doing 2 cubed plus 2. And how much do we want to keep moving this up to? 5. So we've got to be able to move this, we start off with 0, 1, 2. We want to go all the way up to 7. But as we start going to 7, we're actually going to overshoot. What's the largest number we can put here without getting into trouble? We can put 4 or 2 squared. At the 2 squared level, we're fine. When we put in a 2 squared here, 1 kills 2, 3 kills 4, 5 kills 6, 6 kills 7. And so the inductive argument is going to work if we have 2 to the n. We can go up to 2 to the n minus 1. But once we get past 2 to the n minus 1, now the problem becomes a little bit harder. If you look at what happens, though, now we have a shorter number of people with one starting with the gun. And now we're playing games like that. But now it's just with the, whoops, this is probably not a 6, this is a 7. Okay. I don't want to go into too much of the algebra here. I want to just do enough so you have a sense of what's going on and what the key ideas are. There's a lot of really good ideas in this problem. And there is a change, I think, in behavior when you are approaching it like this. Once you add something that's more than halfway, there's a change. Is there anything else we could do? Yes?
Well, don't when you have 2, so if you have n is 12 people, you can kill up to 6 before you have to cycle back.
We don't want to do 12 because 12 is not a power of 2.
Yeah, but that's 2 cubed plus 2 squared.
Okay, so what's your statement again?
So when you increase n,
Oh, you're right. Oh, you're right. You're absolutely right. As we increase n, you're right. We're getting more and more points over here. You're absolutely right. So we will be fine. That's right, because we're growing the number of points here. You're right. Excellent. Thank you. I will claim jet lag. Good. So we are adding more points here, so we will be safe. There was something else we could do, which is not needed here. Well, now we're starting off with 2 cubed plus 2 people. So we're adding more people on this side. And so yes, we've gone through a lot of the people over here. We've killed 4 people, but we also have 4 new people over here. And now at this point, we've now reduced to, we have the correct number of people. And so we'll always have the correct number of people. So I was desperately wanting to do a certain method, but it's not needed for this problem. So thank you. Remember to email me. What I wanted to do is to say we could go down from 2 to the n plus 1. And then just imagine that we started the game a little bit early with more people, and a couple of people died. And just waste a few people like that. It's not needed for this problem. Okay? What is that similar to? where you pretend there's a couple of moves that happen in the first to winnow you down to a certain level. Where have we seen that idea before? Chomp. In Alice is basically going to say, instead of going first, if Bob has the winning strategy, I'm going to just pretend that Bob chose the bottom right corner. And I don't care if Bob wants to move there or not. In my mind, I'm going to declare that to be Bob's move. And then play accordingly. So this is, unfortunately, it's not needed for this problem, but it's another strategy to be aware of. How many of you have seen a proof of the geometric series formula? I think we did that in this class, correct? But we did not do the fun proof, correct?
It was a fun proof because you were doing that.
No. I don't have the basketball net today. I apologize. But I think I promised you at some point that I would show you my favorite proof of the geometric series formula. And I've been saving it for the JosEPHus problem because it's actually related to what's going on here. It's similar to keeping track of who has the gun. Now, for the JosEPHus problem, you can, I think, really understand it matters who has the gun. Okay? Who are the basketball fans in this class? All right. Favorite two players?
I don't like football. I only like college.
Okay. Favorite two college players? Anybody seen? Oh no, I'm blanking on the movie right now. Space Jam. Okay, we'll do Space Jam. As a Celtics fan, I of course prefer to do the classic Larry Bird and Michael Jordan, but I will do not Michael Jordan, Magic Johnson, but I will do Michael Jordan. The first time Cam saw Space Jam, he asked me, "Will Michael Jordan ever play baseball again?" Yes, did not get the point of the movie. So.
I thought Space Jam in 2001 and Space Odyssey were the same movie.
A little bit different.
People would say, like, have you seen 2001 and Space Odyssey? I'd be like, yeah, that's one with the Looney Tunes, right?
All right. How many of you have seen the Michael Jordan, Larry Bird commercials for McDonald's?
Yeah.
There's like a Big Mac.
Right.
There's a Big Mac, and it's not dunking, and they're shooting the basket. The first person to miss does not get the Big Mac. And it's across the highway, through the open window, nothing but net. Off the superstar, incredible shots. And the point is, whoever is the first one to miss loses the game. We'll play a slightly different variant. First one to make the basket wins. Do you want to shoot first or second? First, okay? This should be somewhat similar in spirit to the JosEPHus problem, but not quite as violent. Okay? There is a difference between shooting first and second. You want to be shooting. If you're not shooting, you have no chance of winning. So I will make some semi-unreasonable assumptions. Bird, always a basket with probability P, and Jordan, always a basket with probability Q. I will assume Larry Bird and Michael Jordan do not get tired. I will assume that they are willing to keep shooting baskets as long as possible, and that they will keep playing until somebody wins. In order to make the game interesting, what should I assume about P and Q?
More than one.
Okay, so these are probabilities. And so again, one of the reasons to do this is a way to review some basic probability theory, some basic game theory problems.
You should assume that Q is less than or equal. You should assume that Q
Well, but again, Michael Jordan and Larry Bird are both really good basketball players. I would, this is not like Shaquille O'Neal and Shaquille O'Neal, shooting free throws, where there I would agree that the probability is probably some to one. These are two great basketball players. So you might want to assume maybe they're greater than 0.5. Maybe you might want to assume whoever shoots second has the higher probability, and this is kind of a way to balance things. As a Celtics fan, I will not make that assumption. How large can we assume P and Q?
Less than one.
Probably less than 1, right? If either P or Q is 1, the game is pretty boring. It's really boring if P is 1. All right, what else should we assume about P and Q?
Greater than 0.
Greater than 0. If P and Q are 0, this game will never end. Okay, so we'll assume 0 less than PQ less than 1. Let's let I'm sorry?
Let's have them change based on what shot it is, or based on whether the last person missed or not. Or no, basically.
So first to hit basket wins. Alternate. Bird goes first. We're in Massachusetts, so we'll give Larry Bird the first shot. Okay? So let's let X be the probability Bird wins. So I want a formula to calculate the probability that Bird wins.
P plus.
So this is the probability that Bird wins on his first shot. What's the probability Bird wins on his second shot?
1 minus q times p.
1 minus p times 1 minus q
One
times.
minus-
1 times P.
Okay, raise your hand. Raise your hand. Yeah.
Okay, it would be 1 minus p times 1 minus q times p.
Good. I'm going to write that as R times P, where R is going to be 1 minus P times 1 minus Q. So this means Bird misses, Jordan misses, and then Bird hits. So this is the probability that Bird wins on his second shot. What's the probability Bird wins on his third shot?
R squared.
R squared P. R cubed P dot 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 dot. And so we get X is equal to, I can factor out the P, 1 plus R squared plus R cubed plus dot dot dot. And because of our assumptions on P and Q, this series will converge. In fact, if we wanted to, we could assume P or Q is 0, and the series will still converge. If we knew the geometric series formula, could we calculate the probability that Bird wins?
Yeah.
Yes. We're going to go in reverse. We're going to use this to calculate, to give a proof of the geometric series formula. All right. How many of you have seen this before? There should be at least one person in the class raising their hand. Okay. It's one of my favorite proofs. And it illustrates a key principle in economics and game theory. So who are my econ majors? All right. Have you done any games in econ?
Not much.
Not much? All right. There's a lot of games, and actually the colloquium today on Markov processes is going to be very similar to this. A key fact is the following. I'm going to calculate X another way. So what's the probability Larry Bird wins on his first shot? P. Imagine now we are in the strange world where Bird misses and Jordan misses. What's the probability that Larry Bird wins from this point onward? Raise your hand. So,
The same as.
which is? You can be more concise.
X minus p.
Not X minus, why X minus P?
Because now you've removed, you have the same series but starting at a different point.
Well, I've pulled out the R. So Bird has missed, Jordan has missed. So, which, it's not quite 1 plus R squared. So this is where it's nice to have. It's just X. Why? It's a memoryless process. Remember, this is the idealized Larry Bird, the idealized Michael Jordan. They never tire. Does it matter that they've both missed? Are they going to be psychologically crushed by this?
Maybe.
Who are my college football fans? Anybody know about the really strange play yesterday? Or I guess 2 days ago. So Utah was playing Oregon. Utah was at home. They were supposed to lose. They had a 7-0 lead, 70-yard play. It looks like Utah's going to go up 14-0. And the Utah receiver is showboating, and he spikes the ball, and he just drops the ball and spins it at the 1-yard line. He hadn't quite crossed into the end zone yet. And so some of the people from Oregon go, wait a minute, the referee hasn't raised his hands for a touchdown. And so the Oregon people pick up the ball. There's a convoy of like 4 or 5 Oregon people protecting the guy who runs it back 99 yards for a touchdown in the other direction. And rather than being 14-0 Utah at home, it's now 7-7. And just this, you can just see the crowd deflate. You see the guy, he's pulling his headband over his eyes. He can't. Do you think this is an example of a memoryless process? This is not a memoryless process.
This is what leads to that earlier game.
In a situation like this, it completely changed the dynamics and the tempo of the game. Oregon went on. Now, we have no idea what would have happened otherwise. But in terms of just the heat of the moment, there's a complete shift at this point. Momentum matters. Mentality matters. And as soon as that happened, the game was different. This is the math world. We don't have mistakes. We don't have mistakes like that here. Okay? If Larry Bird and Michael Jordan miss a shot, it's not going to get to them. And so here, it's a memoryless process. This is one of the most important ideas in mathematics. The colloquium talk today by my student G1 on Markov processes is going to be strongly related to stuff like this, to trying to figure out how to handle these memoryless processes and see what's going to happen. We completely bypass the infinite sum. And so now we just have x equals p plus r times x. Well, this isn't so bad. We bring the rx over to the other side. We get 1 minus r times x equals p. So x equals p times 1 over 1 minus r. But we also know it's equal to p 1 plus r squared. What can we conclude? And there's the geometric series formula. What are our constraints?
R less than 1.
So I can take I equals negative 2014 and plug that in. I'm sorry?
Absolute value of r is less than 1. This is greater than 0. It's between 0 and 1.
Mark Twain is a wonderful source of great quotes. Have you heard of his quote about the cat and the stove? So a cat that jumps on a lit stove will never jump on a lit stove again, but will also not jump on a cold one. For each thing in life, take only the lesson you're supposed to. We do not know anything about absolute value of r less than 1. Why are you thinking absolute value of r less than 1?
Because I've seen it.
Because you've seen the geometric series formula before, and that's on your mind, and it should be on your mind. But in the proof we did,
But then we also don't know anything about r equal to 0.
well, if we go back and think about what we were doing over here, if we chose p and q to be 0, what does x equal?
1, 0. It's not.
Well, it depends if it's p or q. If p equals 0, then x equals 0. If p does not equal 0 and r equals 0, then x equals p. We can figure out what's going on in the special case when r equals 0. Okay? In the special case r equals 0, okay, we get 1 over 1 equals 1. Yes?
I guess in this proof, have we waved our hands at convergence of the series? I agree that if it converges, it certainly converges to that.
Right.
But
I think we're trying to argue just from physical grounds that there should be a limiting probability. And that every time we do 2 iterations, Bird has a chance to increase his probability a little bit more.
yeah.
And that you can see every time you do this, Bird gets a little bit more, Jordan gets a little bit more. Bird's is coming up, Jordan's is coming down. It's got to converge.
You could also argue that if they miss every turn, you're having a product of infinitely many things less than 1, and those things are all the same. So the process, in fact, stops at probability 1, and therefore this converges.
Right. But I mean, essentially, the faster way is almost, I think, from this level. But again, this is implicitly assuming that x exists. So with a little bit of work, we can put in the equals 0. So if you want, for a really good homework problem, show that we can take r to be negative. Now, if you think about this, and Jordan and Bird would not be a good example. Which basketball player am I thinking of? Shaquille O'Neal. Okay, we'll do the polite one. How did they spell it?
I think they just slapped the K in there.
Yeah.
Okay.
Why do we?
I'll do it. So I will think about some basketball player who is not so good at shooting free throws. Okay? No matter how bad Shaquille O'Neal is, does Shaquille O'Neal have a negative probability of making a basket?
Probably not.
More than probably not.
She could
And the other
be
No.
like the top guy and end up scoring on the other
Yeah.
That counts, yeah, probably. That's negative.
sports.
The Utah guy did not score on his own team.
He scored, but he helped the other
He,
team.
that's different. We're not going to get too far off top. We're not going to get.
I've definitely scored for the other team before in organized sports.
They never let me play on.
I can believe that. But you're not going to have a negative probability of scoring a basket, right?
Okay.
So no matter how bad you are, and if anybody wants to, we can see if Ali is willing to, allow us to observe some data points. You will not have a negative probability of making a basket. I don't even know what a negative probability would mean. Probabilities are between 0 and 1. This is one of the key things to remember. We are telling a story here. At the beginning of the semester, I think we talked about some stories with binomial coefficients. Telling stories is one of the key ideas in mathematics, but you've got to be careful, what is the story? In this story, we fundamentally have R is 1 minus P times 1 minus Q. Is R allowed to be negative here?
No.
No. There is no way that this story is consistent with R being negative. So my challenge to you, for those of you who want a little bit of a challenge, can you somehow extend this argument and actually allow us to extend now all the way to R being -1? I can extend it a little bit further to certain complex numbers. I cannot extend it to an arbitrary complex number between -1 and 1. I can extend it to some of them. And so the question becomes, how far can you push an argument like this? Okay. So again, why is this related to the problem we started the day with, the JosEPHus problem?
You have to keep track of things.
What do we have to keep track of? And I've seen variants of this problem on math competitions. What are we keeping track of in this game between Jordan and Bird? I'm sorry?
Start.
Who starts with the ball? Who are my Space Jam fans? At the end of the movie when Bill Murray comes in and Bill Murray starts giving the advice of what they're going to do, and then he finds out they're on defense. Oh, I don't do defense. Right? It matters who has the ball. You play differently. So in something like this, we've got to keep track, does Bird have the ball or Jordan have the ball? What if we try to analyze after Bird misses?
That would be like Jordan started.
Then it would be, what would come here? So let's see how well we can do over here now. So X is the probability Bird wins. What is the probability Jordan wins? We could do 1 minus X. Let's assume we're not clever.
Why?
Why do we want to assume? No. We'll assume for now we're not clever. We might have more than 2 people. What if we had Bird, Jordan, and Bugs Bunny, right? Then we would have to have X is the probability Bird wins, Y is the probability Jordan wins, and then 1 minus X minus Y, or Z, is the probability that Bugs wins. So for now, let's just do a Y. We know in the back of our mind, this is 1 minus X. What's the first equation we get for the probability that Bird wins? We're forgetting everything we've done. So we could do the infinite sum, but I claim we don't have to go through the whole infinite sum. It's X equals P plus what?
Q.
I'm sorry? So one thing is we could do P plus Rx, right? We definitely have this as an equation. So R is 1 minus P, 1 minus Q. If we wanted to, we could use that as an equation and solve it. Another equation we could have written down is X is P plus Bird misses. And now what happens?
Jordan loses, so 1 minus 1.
So it could be 1 minus y. Right? So we've got to be very careful. Does everyone agree with this? So, I mean, the probability that Bird wins is just 1 minus the probability Jordan wins. Okay, so we get x is equal to p plus 1 minus p. What's 1 minus y? Oh, crap. These are not the same. This is 1 minus p times 1 minus q. These are not the same. We made a mistake.
But that second line is just for one iteration. There's still, isn't there still infinite
For here?
come after that?
Here? No, it's the memoryless process. So I was really hoping that this would happen, that we would actually make the mistake. Today's lecture would have been a disaster if that hadn't happened. What is the mistake? We should not have two different probabilities of Bird winning. The probability of Bird winning does not depend on how I choose to calculate things. What is the difference? This is the most common mistake in the subject. And it goes back to, I warned you about this multiple times. And for good reasons, they won't let me bring a gun to class, but
It's kind of like Bird can only win when he's shooting.
okay, you're close. Bird can only win when he's shooting.
The two probabilities aren't related. Like the probability that Jordan makes Sebastian isn't related to if Bird makes it Sebastian.
That's not it.
Y equals 1 minus x.
You're close, but what's the definition of y?
Probability that Jordan wins.
When? Y is the probability that Jordan wins, given that,
Given that Bird loses.
no,
Hasn't won yet.
Bird starts.
given that Bird starts with the ball. Given that Bird starts with the ball. Over here, is this probability 1 minus y?
1 minus x.
X is the probability that Bird wins when Bird starts with the ball. 1 minus x is the probability that Bird loses when Bird starts with the ball. What we have here is Bird has shot and missed, and Jordan has the ball.
1 minus y prime.
So it would have to be 1 minus y prime or something like that. If we're in the very special case that p equals q, then life is much easier. Then there's a real symmetry that goes on, and you can exploit that. So I'll let you ponder and think about this. I was hoping I would be able to sneak this all past you. Even with all the warnings about keeping track of who has things. This is the most common mistake people make when they do problems like this, is they lose track of where things are. This is why it's good to introduce subscripts. We could do over here a subscript B to remind ourselves that Bird is shooting. It's the probability Bird wins given that Bird has the shot. Here, y sub b. It's the probability that Jordan wins given that Bird has the shot. And then over here, what I would want is 1 minus y sub j. Jordan has the shot. Well, if I'm not going to capitalize Bird, I'm not going to capitalize Jordan. All right, that's what we would want. Okay, so this is all related to the JosEPHus problem. It's all related to keeping track of who has the gun, who has the ball. Depending on that situation, it is very easy to fall into the wrong chain. Okay.